spreads to the network more quickly. So now with route poisoning, the rule is this. When you lose a route for whatever reason, instead of just deleting it from your forwarding table, tell all of your neighbors that your distance is now infinity. And the rule should make sense. You want to actively tell other people that now you can't reach that neighbor anymore. And try to update their tables with the cost of infinity. And so we can, we can walk through a case here where we had our valid setup here, R3 sends to R2, R2 to R1, R1 to D, and unfortunately this link goes down. So R1 to D goes down. And R1, these host links is going to detect it, and so it sets its cost to infinity. Well, following route poisoning, R1 is going to advertise that infinity to R2 to let R2 know that it has a cost, that R1 now can no longer reach D. And then D is going to update its table and say infinity. And R2 is going to update its table to say infinity to D. And now R2 is going to advertise to R3 and say, hey, my cost to D is now infinity. And that's going to continue onwards. And I just would point out, you actually kind of get this for free in the implementation because as long as you just store infinity in your table, if you were to remove the entry, well, by storing infinity rather than removing the entry, at the next advertisement period, your code by default is going to advertise infinity to the next neighbor. So you'll notice in the implementation, depending on how you implement earlier stages, when it gets time to implement route poisoning, you may not actually have to change much. Any questions on route poisoning? Yeah. Sorry, the next advertisement frequency, is that what you meant? So the question is, why should we even wait until the next advertisement frequency? Why don't we send right away when we hear about infinity? And in fact, that'll be the final optimization where we're going to say exactly that. Why should we even wait till the next advertisement period? Let's just talk immediately when we find out about bad information like that. Any other questions? Yeah. That is a great observation. So in this particular case, because it's kind of to the host, remember that hosts don't participate. They're not like speaking or sending updates. So someone went in and like hard programmed a static route that has a TTL of infinity from R1 to D for the direct next hop. And so R1 needs some sort of method to tell that it's linked to the host went down to update that cost infinity. If, however, it was a link between two routers, then yes, you would have to wait for that initial TTL, like the time to expire. And after that, things can propagate as quickly as advertisements. That's a great catch. Other questions? Yeah. Yes, how is this different than poison reverse? Let me come back to this in just a second. I have a slide on exactly that comparison in just a second. So we now have a solution for our third problem, more or less. Now I realized I just wanted to point one thing out that I had on my slide here that I forgot to say earlier. Split horizon and poison reverse, they really help us with preventing and squashing direct loops. Meaning a direct loop is where I give my packet to you and you give that packet back to me. They're not used for handling cycles, where I give my packet to you, you give it to someone else, and they give it back to me. So we actually need a different fix for those kinds of loops. Just point that out. Okay, so we had, whoops. These are the three questions I listed earlier that were always confusing to me, and I find students get confused with easily. What combinations of these can I use? Which one is best? And route poisoning versus poison reverse, which I'll have a nice chart for. So which combos can I use? Well, luckily this came up as a question earlier. You can't use split horizon and poison reverse at the same time because they conflict. One says say nothing, and the other says say cost infinity. And so your options are, for these two classes of problems, pick one of these solutions or none. And so to be kind of really precise or pedantic, these are all the options you have, where you pick either split horizon, poison reverse, or nothing, and route poisoning, or nothing. You don't need to write these down. You don't need to memorize them. This is just to point out these are the combinations that are possible. And to put it succinctly, something from that set on the left crossed with something from that set on the right. The other question I see people asking is which one is best? And I think there are different tiers to this question. Some people are asking which combo is best, but others are asking actually of the three, which one is the best? And I think it's a slight incorrect assumption when you ask that, because you can't compare all three. Split horizon and poison reverse address one problem. Right poisoning is kind of addressing a different orthogonal problem. And so maybe the better question is what combination of them is best? And to put it shortly, better to use some strategy to solve a problem than none. And it's just rat poisoning or nothing. And for loop prevention, poison reverse was just as good as split horizon, but when loops do arise, direct loops arise, poison reverse squashes them more quickly. So I would say poison reverse and rat poisoning are the best combo. Finally, for comparing rat poisoning and poison reverse, what is the difference? So they are solving, at the end of the day, we're all trying to decrease kind of convergence time, how quickly our network gets back to a valid state. But in my mind, they're kind of solving slightly different problems. And so while their mechanism is the same, of sending infinity, they're triggered by slightly different things. So poison reverse says, if I get an advertisement from my neighbor that has a lower cost than me, than what I currently have to get my destination, I will from now on tell that neighbor that my path to that destination is cost infinity. So I'm going to lie to that neighbor, and only to that neighbor, no one else. Whereas route poisoning says, if I lose a route altogether, not that my route got replaced, but that I lose that route, I'm going to tell everyone immediately that I no longer have a route to this destination. Does that distinction make sense? And so even though they're both sending infinity, they're also doing it slightly differently. For route poisoning, you send infinity to everyone around you to that destination, because you actually have no path to that destination. For poison reverse, you're only going to tell the specific neighbor that you have a route through that your cost is infinity. Everyone else you tell the truth to, whatever that cost is. Does that make sense? Okay. Now, for a split horizon versus poison reverse, I'm going to show one more kind of top-down view on a network that maybe will help you visualize what's going on here. These are from Murphy's slides from an extra little slide deck that he made. We have this network. It looks like this. All of our edges have cost 1, and for now, let's just focus on one destination, because conveniently, as we think about all these things, additional destinations are just more layers of messages on top. The core principle is we can tell with just one possible destination. If we were to look at the best paths to A, that tree would look something like this. And how do we know that these are the best paths? Well, you can just kind of verify that the shortest possible path from 10 to the destination is 1, 2, 3 hops. There's no better path you can come up with on this graph. You could say, well, like, why does 9 go to 3 instead of to 5? That might be an equivalent best path tree, but we break ties consistently here by saying we're going to take the neighbor that has the lower ID. So in a world without split horizon or poison reverse, let's just focus on our router switch 1 here. When switch 1 goes to advertise, it's going to tell everyone it knows, everyone in the world, that it's connected to like each of its direct neighbors, that it has a path to A with a cost of 3. Everyone hears about that. Everyone who is connected to 1 directly. In a world with split horizon, it's still going to tell all of its neighbors, but it's going to be silent to 3 specifically. It won't say anything. Yeah? And in a world with split reverse, it's going to tell everyone, but it's going to lie specifically to 3. So instead of sending nothing, it's going to send, I have a path, but it's cost infinity, so you better not give me any packets. And so if you just kind of step back and take a look, these are all the advertisements that are not sent due to split horizon. And for poison reverse, it's the same exact kind of edges that aren't sent, but instead of not sending, we send the cost infinity. And I'll point out, this looks very similar to something. In fact, this looks identical to the best path tree that we had at the beginning. This should make sense because you don't send your updates along the route that your packet is going to take. And so the updates that you leave out for split horizon or the updates that you send with a cost of infinity, they will be on the same edges as your best path tree. Kind of look from above. Okay, I'm going to cover one more quick topic that I found confusing. I have like 2 slides on this, and then we'll take a break. And then we'll switch over, and Narek's going to talk about Spanish tree protocol. So one other thing I keep seeing people ask, and I wondered this for a while too, was it seems like we need to do routing for both L2 and L3. So which should we be using? We've learned about distance vector. We've learned about link state. We're also talking about learning switches. So what should we be using? Well, L2 is responsible for local packet delivery, and L3 is responsible for global packet delivery. And so the routing problem looks a little bit different in each of these domains. So how does it differ? Well, they both have the same kind of goal of a shortest path and to be resilient to failure. But L3 is a potentially very large network, whereas L2 is all destinations, focused on all destinations in a smaller local network, and it's more plug and play, where people in your local network are going to bring devices, move devices, with minimal support. And so L3 has this property where it has to be scalable. There's this whole question of addressing and how we handle addressing. Whereas L2 is you have a small network, and it needs to be operated with lower cost and like lower setup difficulty. And so we find that distance vector and link state are a better fit for L3, where they scale well, but they require some initial setup. With addressing, which gives us some sort of static configuration. Whereas with a small network, we can use learning switches, which initially flood a packet, and Narek's going to talk about this in a second, and then learn routing after packets get flooded, as we see packets fly by. And so learning switches are a much simpler solution. There's less setup involved. They're a good fit for L2. Distance vector, length state are kind of heavier, and they're better for, they require a little bit more configuration, and so they are a better fit for L3, for a larger network. Yeah? Well, for one, so far up until now, you've had to configure your like attachment to hosts directly, right? Like a network operator had to come in and say, you as a router, you have a direct link to this node and fill in that table, and then let that propagate, for example. Whereas with learning switches, people learn that they're connected, who they're connected to, once someone speaks. Yeah? Yes. There isn't a separate protocol where learning switches are talking to each other. They are learning from actually seeing the data flow by. So if everyone's silent, they're not learning. Before we go off to take a break, are there any other questions on routing overall? No? Okay. We'll take just a 3-minute break, and then Narek's going to come up.